Hello, welcome back. This is going to be our last video related to Chapter 10 and DNA, RNA, protein. Okay, we're going to talk a little bit about HIV here at the end. HIV stands for the human immunodeficiency virus, and this is going to be what really kind of allowed us as scientists to alter our central dogma when we're talking about the flow of genetic information within a cell. Viruses don't necessarily behave the way our eukaryotic cells do, okay? So we've got, right, I've put this up multiple times. You're probably sick of seeing it at this point, okay? But our flow of genetic information within our eukaryotic cells goes from DNA to RNA to protein. Okay, where that can be altered, a lot of viruses use RNA. Oh, squeakiness, as their genetic material. Okay, and we'll use a different pen since that one's squeaky. What that has resulted in now is we can have RNA that can be converted to DNA, all right? Converting RNA to DNA is via a process known as reverse transcription. So what happens when that virus that's made of RNA, and the human immunodeficiency virus is one of those types of viruses, it's going to bring in an enzyme that is unique to the virus called reverse transcriptase. That reverse transcriptase converts the RNA of the virus to DNA. And now what that virus can do is it can take advantage of the host cell's cellular machinery that runs transcription and translation to make more viral particles, okay? The key to this with the HIV virus it has to bring in that protein, that enzyme, reverse transcriptase, because that's not something that's found in eukaryotic cells, okay? And what that HIV virus does then is it takes advantage of the host cellular machinery. Reverse transcriptase converts that viral RNA into DNA, and what can happen with HIV, okay, once the RNA is converted to DNA, that DNA can now integrate into the host cell, okay? So if I draw, I'm just going to draw the nucleus here. This is our HIV, and I'll use a different color. This is our host cell DNA, so this might be your DNA, although I certainly hope not, okay? But a eukaryotic cell. What can happen? That DNA now can make room for itself in the host's DNA, okay? There's another enzyme that's needed for that. The enzyme is integrase. It's what allows essentially that bit of DNA to kind of cut into the host DNA and insert itself, okay? The key here, and I kind of erased something, and that wouldn't necessarily be true. The host isn't going to necessarily lose any genetic information. It just is going to insert somewhere in between. What that does is that now allows the virus to remain what's known as latent, okay? That's how some people can be infected with the HIV virus, but some people will never show symptoms of having it. Some people won't show symptoms for, a year, 5 years, 10 years down the road, because that HIV viral DNA integrated in a place in the genome that isn't actively undergoing transcription and translation. So it kind of lays dormant. But things can change in the cell as environments change. If that region then is transcribed and translated, that cell will start making viral protein, just like it's making the proteins that the cell normally would need, okay? And that's because our genetic code is the same for virtually all organisms. So bacteria use the same genetic code as your eukaryotic cell does. The virus is going to use the same genetic code as your eukaryotic cell does. That's what allows that virus to kind of take advantage, take hold, and end up integrating into the host genome, okay? So because the HIV virus has that reverse transcriptase, it's referred to as a retrovirus because it's going opposite to our normal flow of genetic information, all right? So I just wanted to give you a little bit of background on that because that's kind of an exception to what we've been talking about previously about the flow of genetic information. Viruses don't necessarily follow this flow, okay? So keep that in mind. If you have any questions, please let me know.